In this lab, we're going to be looking at the stoichiometry of a precipitation reaction. In particular, we're going to be looking at a reaction involving a hydrate, which is a substance that also contains water. In this experiment, we are going to continue our focus on building a laboratory safety mindset. We are going to be working with some hazardous substances, so it's important that you pay attention to any kind of hazard warnings that is given to you in your procedure. We're also going to focus on the stoichiometry and the concepts of limiting reagent, theoretical yield, and percent yield. We will also talk about some new experimental techniques, and you'll learn how to do a filtration. And you'll see some of the chemical terms that chemists use to describe chemical reactions. After that, we are going to focus on writing your discussion section in your lab report. Chemical equations are written representations of the process that occurs when chemicals react. So for instance, if two substances are mixed together, we can say, like the blue one there in that picture is A, and the orange one is substance B, and we're going to mix them together and see what happens. So at the top, you can see a generic chemical equation using A and B, capital A and capital B as our substances. This chemical reaction is going to be similar to a recipe for how this new substance is going to be formed, as it tells us what substances are involved, how much of each substance is involved, and what to expect when the reaction is over. It's broken up into reactants, which are on the left, and products, which are on the right. Reactants are your starting materials. They are the substances that you're going to start off with, and they're often the ones that are found written in the materials list of your procedure. Products are what you end up with. They are not listed in your materials list, as they didn't exist when you started out. The coefficients, those are those little case letters, tell you how much. It's like the 2 when you're thinking about 2 cups of oats in my cookie recipe. And just like with my cookie recipe, it says if I need to make an adjustment, if I don't have 2 cups of oats, the chemical reaction is going to tell us how much of each of the remaining substances we're going to need to have to produce a particular amount of product. So if I need 2 cups of oats to make 1 batch of cookies, that's great. If I don't have 2 cups of oats, instead, let's say I have 1 cup of oats, then I need to reduce the amount of flour, sugar, Crisco, eggs, and so forth. And that will also affect how many cookies I'm going to make in my batch. Okay, so instead of making a full batch of cookies, because I only have half the amount of oats, I'm going to only be able to make half of our recipe. And the same thing is going to apply with chemical equations.
One of the concepts that we will be talking about in this experiment is that of limiting reagents. Whenever we have 2 reactants, we need to look at and see which one limits the amount of product that we've formed. This will also help us to determine the limiting reagent. Whenever you're looking at limiting reagents and trying to figure them out, try to think about making a sandwich. If you have 6 pieces of bread and 3 slices of turkey, you can make exactly 3 sandwiches using 2 slices of bread each and 1 slice of turkey. However, if you had 20 slices of bread and only 3 slices of turkey, turkey would be your limiting reagent because you cannot make more sandwiches once all of the turkey is used up. So the turkey then is your limiting reagent and the bread is your excess reagent. When we're looking at chemical reactions, we have to do some calculations to determine what the limiting reagent is. You did the same thing with the sandwich analogy, only you did that math in your head. The first thing we need to do is convert from our starting unit, whether that's grams or milliliters, to moles. Once you're in moles, you can switch between different substances or reagents using the balanced chemical equation. So you always want to make sure that that chemical reaction is balanced before you begin. You can then compare between different reagents to see how much of the product you were able to produce, because whichever starting material produces the least amount of product will tell you which is your limiting reagent. Remember, the limiting reagent is the reactant which produces the least amount of product. Let's look at an example. If 100 grams of aluminum and 200 grams of iron oxide, according to the reaction shown below, react together, how much aluminum oxide will be formed. So we see that we have our reaction written out. Al plus Fe2O3 yields Al2O3 plus Fe. And a note that says that it's unbalanced. So the first thing we're going to do is check and make sure that this reaction is balanced. Well, we see that on the left side we have 1 aluminum, and on the right side we have 2. So we're going to need to put a 2 in front of the aluminum on the left. So now that that's balanced. Okay. If we look at our iron, we see on the left side there are 2 irons, and on the right side only 1. So we're going to need to put a 2 in front of the iron on the left. And then let's check really fast our oxygens. We have 3 oxygens on the left side and 3 oxygens on the right side. So now we have a balanced equation. So let me summarize what we had on the previous slide real fast. We have the balanced chemical reaction of aluminum reacting with iron oxide to form aluminum oxide and iron. And we're given 100 grams of aluminum and 200 grams of iron oxide. I've gone ahead and calculated the molar masses, and those are shown below. You can calculate the molar masses using the values found on your periodic table to verify my values. So the first thing we need to do is look at one of our reactants. So let's start with the aluminum. If we start with 100 grams of aluminum, we know that we're going to convert to moles. So since grams is on top, we're going to want grams on the bottom. So we're going to write in 26.98 grams of aluminum for 1 mole. If we look at our balanced chemical reaction, we see that for every 2 moles of aluminum, we form 1 mole of aluminum oxide. Then we can convert back to grams using the molar mass. So since moles is on top, we're going to put moles on the bottom. Moles of aluminum oxide for every 101.96 grams of aluminum oxide. I'm going to check real fast that all of my units cancel out. So we started off with grams of aluminum on top. That's going to cancel with grams of aluminum on bottom. Moles of aluminum cancels with moles of aluminum. Moles of aluminum oxide cancel with moles of aluminum oxide, leaving us with grams of aluminum oxide. And if we work out the calculation, we get 189 grams of aluminum oxide. Well, that tells us what we'll produce if aluminum was a limiting reagent, but at this point we still don't know whether it's aluminum or iron oxide, so we need to do a similar calculation with the iron oxide. So we started off with 200 grams of iron oxide, and again we want grams to cancel out, so we're going to use the molar mass. 159.7 grams of iron oxide in 1 mole. We want moles to cancel out, so we're going to look at our balanced chemical reaction. We see that we have 1 mole of iron oxide for every 1 mole of aluminum oxide. And then again, we want to convert to grams, so we put moles on bottom again and grams on top. Again, we want to check really fast that all of our units cancel out. So we have grams to grams, moles to moles. Moles of aluminum oxide leaves us with grams. And if we work all of this out again, we get 128 grams of aluminum oxide. Therefore, the iron oxide, since it produced the smallest number of grams of aluminum oxide, the iron oxide limits the reaction and is therefore the limiting reagent. One thing you need to notice is we're starting with more iron oxide, but it ended up as our limiting reagent. We can't just look at the moles or the mass of a substance to determine whether or not it's the limiting reagent. You need to look at how much product you can produce. The maximum amount of product that you can produce from this reaction is 128 grams of aluminum oxide. Now we're going to talk a little bit about yield. In the previous example, we said the maximum amount of aluminum oxide we can produce was 128 grams, and that would be our theoretical yield. So based on the stoichiometry, the most we can possibly make is 128 grams. This is a calculated value. Our actual value is what we really get when we go into the lab and we perform the experiment, and this is usually less than the theoretical yield. Now, for our previous example, we had 128 grams that could potentially be produced. That's our theoretical yield. That is the maximum amount of product that can be formed. When we look at an experiment performed in the lab, we also have to be concerned with the actual yield, which is the amount that is actually produced. This number is less than the theoretical yield. Depending upon how your experiment went, it may be much less than the theoretical yield. We need to remember, no matter what we do, we can never have an actual yield that is greater than our theoretical yield. If you get an actual yield that's greater than your theoretical yield, either your sample isn't dry or there's some other product in your mixture. Now, it's important to understand how this could happen, so it's a good idea to look at the procedure and see where this could have gone wrong. This is part of your error analysis in your discussion section as part of your lab report. Let's look at a quick example on how to determine our yield. Remember, our theoretical yield we calculated previously was 128 grams, but let's say we only obtained 105 grams when we did the reaction. What's our percent yield? Percent yield is defined as being the actual yield over the theoretical yield times 100. So for our example, the percent yield is our actual yield, 105 grams, divided by our theoretical yield, 128 grams, times 100. So if we work this out, our percent yield is 82.0%. That's pretty good. We formed 82% of what we could have or should have formed compared to the theoretical yield. Think of it like an exam score or when you're calculating your final grade. You could score 100 points, but you don't always do that. Your actual score divided by your theoretical score equals your grade. So in our actual yield divided by our theoretical yield gives us our percent yield. A few reminders for this experiment. Record the actual volumes used for all your liquids. And remember, you should always estimate 1 decimal place beyond the markings on the glassware. For example, if you're using the 10 milliliter graduated cylinder with marking to the 10th mark, you can actually get 2 decimal places because you can estimate the difference of the volume level between the 2 markings on the glassware. It's important that you record the actual volumes and masses that you use. The values listed in the lab manual are only approximate. You do not have to get precisely what the lab manual states. You should be generally close to it, and you should record what you actually used. Also, make sure you're using distilled water to avoid introducing additional impurities into your reaction. Record the mass of the filter paper in the watch glass so that when you weigh the filter paper in the watch glass with your sample, you can subtract those 2 values so that you know what the mass of your sample was. Make sure that you let your sample dry completely in the oven before you take the mass of it. If your sample is wet, it will be heavier than you expect and will result in a percent yield greater than 100%, which we said previously was physically impossible. And also, it makes it a little bit more challenging to write up your lab report. As always, if you have questions, see your TA, go to the Learning Center, or talk to the lab supervisor.
If you have any questions, please make sure to reach out and ask them on our Course Piazza site. Contact your TA, visit the General Chemistry Learning Center, or reach out to your lab supervisor. Thanks.